Hello students, I am Professor Navneet Kaur, Associate Professor in Department of Electronics and Communication, Sagar Institute of Research and Technology, Bhopal. Today I will be taking lecture on subject digital communication. The topic which I will be taking is line encoding techniques. Line encoding is digital to digital encoding or conversion, where there is a representation of a digital information by a digital signal. When we transmit data from computer to another computer, both the original data and the transmitted data are digital. In this type of encoding, the binary ones and zeros generated by a computer are translated into a sequence of voltage pulses plus V and minus V that can be propagated over a link, and it will be received by another computer system, which will be again decoded as sequence of zeros and ones and will be interpreted by the receiver computer. Now, before dealing with the line encoding technique, we should know some basic definitions like signal element and data element. Data element is the smallest entity that can represent a piece of information, which is normally a bit, whereas a signal element is the shortest unit of a digital signal. We can say that the data elements are what we need to send, and signal elements are what we can send. Now, difference between the data rate and the signal rate. Data rate is the number of data elements sent in 1 second. Since data elements are represented by bits, its unit is bits per second, and it is also called bit rate. Whereas signal rate is the number of signal elements transmitted in 1 second. Its unit is the baud. Signal rate is also called pulse rate, modulation rate, or the baud rate. There is a relation between data rate and the signal rate, which is given as signal rate is given as product of C, which is the case factor, and N, which is the data rate, which is given as bits per second, and R, which is data elements per signal elements. Now, there are some examples. Here we can see the difference between the signal element and the data element. Now, in first figure, we can see that the data element is represented by bit 0, which is represented by high voltage level, whereas bit 1 is represented by low voltage level. That is, there is one data element for one signal element. So in this case, small r, which is the ratio of the data element to the signal element, is given as 1. Now in second figure, we can see that bit 0 is represented by two signal level, that is from low to high. So in this case, data element is 1, whereas signal elements representing this data element is 2. So small r is given by 1 upon 2. Now here we can see that our data consists of two bits, that is 1, 1, 0, 1, and so on. Here 0, 1 is represented by low voltage level. So in this case, the data elements consist of 2 bits, whereas signal element is 1. So there are 2 data elements per one signal element. So small r is given as 2. Now in last example, we can see that there is a data element 1101, which consists of 4 bits. So there are 4 data elements. Now this data element 1101, this information is represented by 3 voltage level, that is high to low to 0. So in this case, there are 4 data elements per 3 signal elements. So small r is given as 4 by 3. Now, before going into the details of the line encoding, we should know what is baseline wandering. In decoding a digital signal, the receiver calculates a running average of the received signal power, and this average is called baseline. The incoming signal power is always evaluated against this baseline to determine the value of the data element. Ideally, There should be no baseline. A long string of zeros or ones can cause a drift in the baseline, which is called baseline wandering, and it makes difficult for the receiver to decode the transmitted information correctly. A good line encoding scheme needs to prevent baseline wandering. Now, baseline wandering is defined by the DC component. When the voltage level in the digital signal is constant for a while, the spectrum creates very low frequencies. These frequencies are called DC components, and it creates problem for a system that cannot pass low frequencies or a system that uses transformer coupling. For example, a telephone line cannot pass frequencies below 200 Hertz. To correctly interpret the signals received from the sender, the receiver bit interval must correspond exactly to the sender bit interval. That means there should be synchronization between the receiver and the transmitter clock so that the bit intervals are interpreted correctly. Now, in this case, there is a requirement of self-synchronization in which the digital signal includes timing information in the data being transmitted. This can be achieved if there are transitions in the signal that will alert the receiver in the beginning, middle, or end of the pulse. Now, coming to the classification of line encoding methods. There are three types of line coding method: unipolar, polar, and bipolar. Now we will see all these three methods in detail. Now, unipolar method is defined as NRZ, which is non-return to zero method. Now, polar method is again of three types: NRZ, which is non-return to zero; RZ, return to zero; and biphase. Biphase is again of two types: Manchester and differential Manchester. And bipolar line coding method is categorized as AMI and zero-ternary. Now, in this lecture, we will consider unipolar and polar encoding methods. Now, first, unipolar encoding. It is the simplest encoding method. It is almost obsolete today, but its simplicity provides an easy introduction to the concepts developed with more complex encoding systems. Here, the signal uses only one polarity to represent data. Bit 1 is represented by positive voltage and bit 0 is represented by zero voltage. Now, synchronization problem can occur when data stream includes long uninterrupted series of ones or zero. So this encoding method has DC component problem as only one polarity is used. Now, the advantages of unipolar encoding: it is very simple to implement and it requires less bandwidth for transmission. Disadvantages: that it has DC level component. It does not have any error correction capability. It does not possess any clocking component for self-synchronization, and long string of zeros causes loss of synchronization. Now, coming to polar encoding. Polar encoding, as I have already discussed, it is of three types: non-return to zero, return to zero, and biphase encoding. Now, first, non-return to zero encoding. Here, the level of the signal is always either positive or negative. It will not take level 0. NRZ is of two types: NRZ level and NRZ inversion. Now, in NRZ level, the level of the voltage determines the value of the bit, whereas in NRZI, the inversion or the lack of inversion determines the value of the bit. Now, first we will see NRZL encoding. Now here, binary 1 is represented by high voltage plus V, and binary 0 is represented by low voltage, negative voltage minus V. So here bits are represented by levels plus V and minus V. The advantage is it is simple to implement. It has no DC component because two polarities are used, positive and negative. The disadvantage is that it does not have self-synchronization capability. neither it has an error correction capability. And long strings of ones or zero causes synchronization problem. Now NRZ inversion. Here the inversion occurs when the bit 1 comes, whereas there is no inversion when the next bit is 0. So here we can see that initially the binary 1 bit is represented by high level. Now since the next bit is 1, it will have inversion from plus V to minus V. Now again the next bit is 0, there will be no inversion. Then 0, there will be no inversion. Now coming to 1, there will be inversion. Now again the next bit is 1, there will be again inversion. So the inversion occurs whenever the next bit is 1. So here the synchronization problem is solved in case when there is long sequence of ones, because inversion occurs whenever there is a sequence of 1. It has no DC component because it has both polarities, positive and negative. The bandwidth of the signal is FB by 2. Now coming to polar, return to 0. Here the binary 1 is represented by plus V voltage for half of the bit interval and 0 voltage for second half of the bit interval. Whereas 0 is represented by minus V for half of the interval TB and 0 for second half of the interval 0. So it fills only the first half of the time slot, returning to 0 for the second half. Advantages of polar return to 0, it is simple to implement and it has no DC component because both the polarities are used. Disadvantage is that it does not have any error correction capability. That bandwidth is twice as that of polar and NRZ, and there is a transition at the middle of the bit interval which increases its bandwidth. But this transition at the middle of the bit interval, it causes self-synchronization, which is an advantage. Now coming to biphase line encoding method. As I discussed, it is of two types, Manchester encoding and differential Manchester encoding. Now, in Manchester encoding, 0 is represented by plus V to minus V transition, whereas 1 is represented by minus V to plus V transition. So there is transition at the middle of the bit interval, which causes synchronization. Whereas in differential Manchester, there is no inversion at the beginning when the next bit is 1. Whereas there is inversion at the beginning when next bit is 0. So here we can see that since the first bit is 0, say initially the level is at plus V. Since next bit is 0, there will be inversion from plus V to minus V. So it will have minus V to plus V transition. Now since next bit is 1, there will be no inversion. So we'll have plus V to minus V transition. Now since the next bit is 0, first initially there will be transition from minus V to plus V, and then it will go from plus V to minus V for a bit interval TB. Now, polar biphase. In Manchester and differential Manchester encoding, there is a transition at the middle of the bit interval which is used for self-synchronization. There is no DC component because it uses both polarity, positive and negative. And since there is a transition in the middle of the bit interval, the bandwidth is twice as that of the polar non-return to 0. Now this is all for today's lecture. Thank you.